Of Unit 2. Unit 2 is all about quadratic functions and equations. In this video, we're going to talk about learning target 4a, which is all about graphing the quadratic function as well as using transformations. By the end of this lesson, you will be able to graph and describe how a quadratic function in vertex form has been transformed from the parent function y equals x squared. We will also be able to identify the vertex, the axis of symmetry, determine if the vertex is a maximum or minimum value, and find the domain and range of a quadratic function in vertex form. So let's start with what a quadratic function is. So the quadratic function, the most simplest form of it, would be y equals x squared. And that's going to be our new parent function that we're going to be looking at for this unit. So let's graph that parent function. So if we take y equals x squared, we've got a few points for us to substitute in. Let's start by substituting in -2. So I'm going to take -2, and then we'll be squaring that. I do want to make sure that that -2 is in parentheses, since if I don't have the parentheses there, it would mean that I'm only squaring the 2 versus the entire -2. And since I'm subbing in -2 into that x, I want to be squaring that entire number. So -2 squared is -2 times -2, which would give us a +4. Our next x value that we're subbing in is -1. Again, I want to make sure I have that in parentheses so that we're squaring both the negative sign and the 1. -1 squared is -1 times -1, which will give us a +1. My next x value to sub in is 0. 0 squared is going to leave us with 0. Our next value will be a 1, and in this case you're starting to notice that I'm not putting parentheses around it because they're not needed since I don't have those negative signs. 1 squared is 1 times 1, which leaves us with 1. And then our last x value to sub in would be 2, and 2 to the second is 2 times 2, which leaves us with +4 as well. So this gives us a couple coordinate pairs to look at on this graph. So our first coordinate pair will be that -2, 4. We'll have this -1, 1. We'll have 0, 0. We'll have 1, +1, as well as 2, 4. So if we plot those on our graph here, we're going to start to see that we're getting a different shape than we did with the absolute value graph, which we learned about in our last unit. And instead, we're getting this shape that's going to be curved. And this shape here is actually going to form a U-shaped graph, so it curves out and around. I don't have any straight lines like we did in Unit 1, but instead I have this nice U-shaped curve, which we call a parabola. So y equals x squared is a quadratic function, but its graph is a U-shaped curve that we call a parabola. Just like the absolute value graph, we have an axis of symmetry. And so this parabola graph is symmetric about the vertical line x equals 0. So if we draw that in on our graph, remember our axis of symmetry is that line where if we were to fold our graph in half, we would get a mirror image on either side. So we still have that axis of symmetry at x equals 0. A parabola also has a vertex, and for the parent function, that vertex is right there at 0, 0. And in this case, this happens to be the lowest point on the graph, and we would call this a minimum since it's the lowest point. Later on, once we start to talk about transformations, we're going to see how this vertex can change, and maybe if we do certain transformations, the vertex is no longer a minimum, but instead could become a maximum on our graph. Our domain for a quadratic function is all real numbers, since I can sub in any x value into x squared and get a real number out of that. So I can sub in the negatives, 0, and the positives. And our range here, we notice that when I sub in any number into x squared, when we square any number, we always get a positive value, which is why our range then is no longer going to be all real numbers, but instead it's just all the positive numbers, or we could also get 0, since 0 squared gives us 0. Now, of course, as we apply the transformations, we're going to see our axis of symmetry, our vertex, and our range all change according to our transformations. So let's review our 4 transformations. So again, we have our horizontal transformations, which would be the first set that we apply. That would be our right or our left transformations. That happens inside the function. And so since our parent function now is y equals x squared, then those transformations happen inside the squared, so the -h and the +h are inside those parentheses. Our second type of transformation is a vertical stretch or compress. And that happens when we take this stretch or compress factor, which we call A, and we multiply it to our parent function x squared. Remember, it's a stretch if a is bigger than 1, and it's going to be a compress if a is less than 1 but bigger than 0. Our third type of transformations is our reflections. We have two types, a reflection over the x-axis, and that's when we multiply the negative sign outside the function. So in this case, the negative sign is not being squared since it's outside that x squared. Then our second transformation is over the y-axis, and in that case the negative sign is inside the function, which is why it's inside the parentheses. So not only are we squaring the x, but we're also squaring that negative sign. And just as a reminder, these guys are not the same because we're missing those parentheses in that first one. So in this case, it's only the x that's being squared. So if I wanted to add parentheses to really see that distinction here, we could rewrite this as that negative times the quantity x squared. But those parentheses are not needed, so we're not going to be writing those. That would just be the same with the negative sign on the outside. Then our last type of transformation is our vertical shifts, which is our up or our down, and that happens outside the function, and that's when we're adding k or subtracting k. So our transformations are still the same that we learned in our last unit, but we're now just applying them to a different parent function of y equals x squared. Just like in our last unit, we're going to use the transformations to help us graph. So we need our start points, but since our parent function has changed, our start points will also change. And I want to scroll back up so we can see the parent function graph here. So on this parent function, since we're getting this U-shaped curve, we actually are going to need all 5 of these points to be used as our start point. And the reason being is that I need to make sure I get that complete curve there, and if I only take the 3 points with the vertex and 1 on either branch here, I'm not going to know for sure if the graph curves. So now I need to add in this -2, 4 and this 2, 2 point, so I make sure that I get this entire U-shaped curve. So what that tells us is then we're going to again use these transformations to help us graph, and we're going to use -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 as our start points. And again, these are coming from our parent function that we had up above, and those are the exact same 5 points that we used to plot and graph y equals x squared. And since we have a new parent function now, that's why we have new start points that we're working with. And these 5 points are coming from that y equals x squared. So let's look at our first example here. So in the following examples, what we're going to do is we're going to describe the transformations and then use them to graph. And lastly, we'll be stating the domain and the range. So for our first example here, we have y equals x minus 3, the entire thing squared, minus 5. The first thing we need to do is we need to list our transformations. Why don't you guys pause the video right now and list our transformations for this first example, and list them in order. So for this first function, we have 2 transformations. The first transformation is that we're going to the right 3, and that's coming from that x minus 3 inside the squared. Our second transformation is that minus 5, which is telling us that we are going down 5. Now, just like we did with the absolute value graph, we're going to apply these transformations to our start points. And this time, since we have x squared as our parent function, I'm going to write that on the side just as a reminder that y equals x squared is the parent function now. We have different start points than we did for the absolute value since we're dealing with a different parent function. So our start points for this guy is going to be that -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And I want to remind you guys that those are coming from our parent function, where I'm taking the x value and I'm squaring it since that's what's in our parent function. And that's how I'm getting the 4 from the -2 squared, the 1 is coming from the -1 squared, the 0 is coming from the 0 squared, the 1 is coming from the 1 squared, and the 4 is coming from the 2 squared. So these points are coming from our parent function. Now we can apply our transformations just like we did before. When we go to the right, that's changing our x-coordinate, and we're adding 3 to that x-coordinate. So let's go ahead and apply that first transformation here. And so when we add 3 to -2, we're going to end up at +1, When we add 3 to negative 1, we'll end up at positive 2. When we add 3 to 0, we're at 3. And then we're going to be at 4 and 5 by adding 3 to the final two x coordinates. Now, since we were just going to the right, that is not changing the y coordinate, so I can go ahead and rewrite those points. And then apply our last transformation here. Our x coordinates are not going to change. Since our last transformation is a vertical shift, that will only change the y coordinates. And since we're going down 5, we're going to be subtracting 5 from those y coordinates. So with our 4's, when we subtract 5, we're at negative 1, and that will be true for both the first and the last point. When we're at 1 and we subtract 5, we're at negative 4. And then when we're starting at 0 and we subtract 5, we're at negative 5. Now that we've applied both of our transformations, we're going to go ahead and graph these final points then. And we want to keep in mind that since our parent function is y equals x squared, we should be getting a U-shaped graph. So when we plot these, we want to make sure we're not connecting them and drawing straight lines between them, but we're getting this nice smooth curve. So as we go to plot these points, we're at 1, negative 1, 2, negative 4. We're at 3, negative 5. Then we're at 4, negative 4, and 5, negative 1. So we can see that U-shaped curve that we could connect together. And here you'll notice I'm not using any straight lines. I'm making that nice smooth curve on both the left and the right side. And this graph does, of course, keep going up from there. We can see on this graph that we still have an axis of symmetry that would be running straight through that vertex. And we can see our vertex down here is at 3, negative 5, since that's where 0, 0 started. Or that's where 0, 0 ended up after we applied the two transformations. Now the last thing we have to find is our domain and our range. Our domain for our parent function being y equals x squared was all real numbers. So no matter what crazy transformations we do, we're still going to end up with all real numbers as our domain. But for our range here, that's going to depend off of what happened with our transformations. And our range is affecting the y values. And so it started off with y being greater than or equal to 0. But as we apply the transformation, right 3 doesn't change it. But when we go down 5, we're subtracting 5 from all the y's. So that tells me that my range ended up being at y is greater than or equal to negative 5. And we can see that from the graph, since negative 5 is our lowest point on the graph down here, and everything else is above that. So that's why we have y is greater than, and then we have the equals to, since we do reach negative 5 being our vertex on the graph. So there's our first example where we identified the transformations, used our start points for our parent function being y equals x squared, applied both transformations, and then graphed those final 5 points, connected them together, making that nice U-shaped curve. From there, we can then identify our domain and our range. Let's look at our next example. So in our next example, we have y equals negative, then in parentheses, x plus 1 squared plus 2. Why don't you guys pause the video and list all the transformations for this function. So to check our transformations, our first one is going to be that plus 1, which is telling me that we are going left 1. Our second transformation is the negative sign out front, which is a reflection over the x-axis. And our last transformation is coming from that plus 2, which is our up 2. So our vertical shift. Again, here our parent function is now y equals x squared. Since we have that squared power, there in our equation, so that's how I'm identifying x squared as our parent function. So for y equals x squared as our parent function, we have those 5 start points. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and then 2, 4. Oops. See if those will write. There we go. So we have to apply our 3 transformations to these. So let's think about what each one of these transformations does. So left 1 is a horizontal shift that's going to affect our x coordinate. And we're going to be subtracting 1 from all the x's. What about a reflection over the x-axis? How does that affect the coordinates? So when we reflect over the x-axis, we're multiplying all the y's by a -1. Since we're flipping over the x-axis, our x value is not changing, but our y value is changing signs. And then lastly, our up 2 is affecting our y, since that's a vertical shift, and we would be adding 2 to all of the y's then. So let's apply these transformations. So why don't you guys pause the video right now, apply all 3 transformations, and then we'll check it together at the end. So applying our first transformation here, we're subtracting 1 from all of the x's. So we're at -3, -2, -1, 0, and 1. Since that left one was affecting the x's. Now our y's don't change in this case, since we were only changing the x's. For our second transformation now, I'm reflecting over the x-axis, so I'm multiplying all the y's by a negative. So I'm going to rewrite those x coordinates and then multiply all the y coordinates by a -1. So the 4 will go to -4, the 1 will go to -1, 0 will still stay at 0, and then the 1 will become a -1, and again the 4 will become a -4. Then our last transformation, let's see if I can fit it here, is going up 2, which is changing the y's. So again, those x's can just be rewritten here. And then for each y coordinate, we're going up 2, so we're adding 2 to all of those y's. So -4 is going to end up back at -2 then. -1 will be at +1, 0 will go to 2, -1 will go to 1, and -4 will be at -2. Now these are the 5 points that we graphed since we've now applied all of our transformations. So I have -3, -2, -2, +1, -1, 2, 0, 1, and 1, -2. So now these 5 points are flipped upside down, and that's happening because we have that reflection over the x-axis. We know that our vertex started out at 0, 0, so wherever 0, 0 ends up, which is at -1, 2, this makes sense that this would either be the highest or the lowest point depending on which direction our parabola is facing. And since our U shape started facing upright, but then because of that reflection over the x-axis, it flips that parabola upside down, so my vertex now went from being the lowest point on our graph to being the highest point on our graph. So I'm still going to get this U-shaped, it's just going to be flipped upside down. So I'm drawing that, oops, that's not going through the point there, so I'm drawing this nice U-shaped curve to the best of my ability on here. Of course, it'd be a lot easier with paper and pencil. The last thing we have to identify is our domain and our range. Our domain for our parent function started off as all real numbers, so no matter what transformations we do, that will stay at all real numbers. Our range, however, let's think about what happened here. Our range started out being y is greater than or equal to 0. When I go left 1, that's affecting the x's, so that's not changing our range. When I reflect over the x-axis, though, that's multiplying all of our y coordinates by a -1. So in this case then, instead of being y is greater than or equal to, that's going to flip that inequality since I'm multiplying 0 here by a -1 when I reflect over the x-axis. And so 0 times anything is still 0, but that inequality sign is going to flip. And we can see that in the graph because instead of the vertex being the lowest point, when we reflect it, the vertex now becomes the highest point. So everything is less than or equal to that. Then our last transformation was that up 2, which means that I'm adding 2 to all of my y's, so I end up with a range of y's less than or equal to +2. So we can see a couple of these transformations in action through these last 2 examples. Let's talk about what happens generally here. So we have 2 forms for quadratic functions. Quadratic functions can either be in standard form or they can be in vertex form. And throughout this unit, we're going to use both forms, but right now I want us to talk about which form is more helpful for different scenarios. So vertex form here, which is the form that we've seen in this entire video so far, is really helpful when we're graphing, which is why we've seen everything in vertex form thus far. So Formally, the vertex form of a quadratic function is f of x equals a times parentheses x minus h squared plus k, where a, of course, is non-zero. Otherwise, I would just end up with 0 times everything, which would just give me 0 plus k, which would no longer be a quadratic function. So here, the a, the h, and the k should look familiar. These are coming from our transformations. That a is our stretch or compress factor. It could also be a reflection over the x-axis if it were to be negative. This h is our horizontal shifts, and the k is our vertical shifts here. And that h is happening inside the function, and that k is happening outside the function. From this, I can always identify what my vertex is, which is why we call this vertex form, because it's so easy to find our vertex from here. So when I have x minus h, I've gone to the right h units, and then the plus k is telling me that I've gone up k. That leaves my vertex at h comma k. The reason being is my vertex started at 0, 0, and as I apply the transformations, I'm always going to end up at my horizontal shift for my x value, comma, my vertical shift for my y value. And the reason this happens is because of the order in which we apply the transformations. The fact that our stretch or compress, if there was one, always comes first, before our vertical shifts, then we would be taking 0 and multiplying it to a, but we know that that still keeps it at 0, and then we're adding the k from there. The other thing that I can find from vertex form is, since I have the vertex, we know the axis of symmetry runs directly through the vertex and is the vertical line then x equals h, and that matches up with the x coordinate in our vertex being h, as well as x equals h in our axis of symmetry. The other thing I can actually determine is if my vertex is going to be a maximum or a minimum. So if a is a positive number, so if my stretch or compress factor here, whether it's a stretch or compress, if that number is positive, then there's no reflection over the x-axis, which means our graph is facing upward. So it would be this upward facing parabola here. Our vertex then is going to be a minimum since it's at the bottom of this graph here. It's the lowest point. That also tells us that our range is going to be y is greater than or equal to k. Since our vertex is a minimum, everything's above it, so we have greater than or equal to. And then the k is coming from the vertex itself, since that is the y coordinate of our vertex. Now, if this a value were to be negative, that would mean that there's a reflection over the x-axis, which means the graph has been faced upside down, and now our vertex is actually a maximum. It's the highest point on this graph. How that affects is that changes our range. So instead of y being greater than or equal to, when we reflect over the x-axis, our vertex becomes a maximum, so our range is now y is less than or equal to this k value. And again, the k value is coming from that vertex itself, and the less than or equal to is coming because of that reflection, just like we saw in example 2. So we get a lot of information out of vertex form. Now, standard form, on the other hand, is not really helpful for graphing at all, but it's going to be really helpful as we start to solve quadratic equations. So a large part of this unit is not going to be about graphing. It's instead going to be about solving all these different types of quadratic equations, and we're going to want all of our quadratic equations in standard form then. So standard form of a quadratic function is f of x equals a times x squared plus b times x plus c, where again a is not equal to 0. And you're going to notice now, instead of having h and k, I have these b and c's. So a is still the same number that it was in vertex form. That's the one thing that those two forms share in common. B and c are just some other real numbers that we get, where if we were to kind of FOIL out vertex form and combine all of our like terms and write them from highest power to lowest power, that would give us our standard form then. Let's look at our last examples for this section. So now we're going to focus on not graphing. We just want to practice finding the vertex, the axis of symmetry, determining if the vertex will be a maximum or minimum, and then find the domain and range. So let's look at our first function. We have y equals 3 times x minus 4 squared minus 2. I want you guys to pause the video right now and state all of your transformations, because those are going to help us think about how we find these 5 items. So we have 3 transformations here. Our first transformation is coming from that x minus 4, which is telling us that we are going right 4. Our next transformation is that 3 that's being multiplied. That's telling us that we are stretching by 3, and that's a vertical stretch. And then the last one is the minus 2, which tells us that we are going down 2. Now our vertex, I can read out of this equation, since this is our vertex form, which remember in general is y equals a times x minus h squared plus k, and we were able to read out of that our vertex would be at h comma k. But I also want to relate this back to our transformations. So by looking at my equation, I can tell that my vertex is going to be at 4 comma negative 2, but let's verify that using our transformations. So our vertex starts out at 0, 0, and when I apply our first transformation of going right 4, I'm adding 4 to the x component, so I end up at 4 comma 0. And then when I apply my second transformation and I stretch by 3, I'm multiplying the y component by 3, but 0 times 3 is just going to still leave us at 0. And then our third transformation is that down 2, and I subtract 2 from my y coordinate, which leaves me at 4 comma negative 2. And that matches up exactly with what I was able to read out of my equation using this generic vertex form information. Now our axis of symmetry, remember, is that vertical line that runs through our vertex. So this will be at x equals positive 4 then. Since there was no reflection over the x-axis, I know that my graph is still facing upwards. The other reason I know that is I can look at the a value. So in my equation, our a value is the number in front of the parentheses, so our a value is 3. Since that number is bigger than 0, it tells me that I had no reflection, so my graph is facing upward. And because of that, I know that my vertex then is going to be a minimum on this graph. And this information again is coming from what I discovered out of standard form by looking at if a is bigger than 0 or if a is less than 0. Now our last two things are our domain and our range. Our domain again is going to be all real numbers. And our range, let's think about what happened. It started off at y is greater than or equal to 0. When I went right 4, that doesn't change it. When I stretched by 3, I multiplied the y component by 3, but that still kept it at y is greater than or equal to 0. And then from there I add 2 to all the y components, and I end up with y is greater than or equal to 2. This also matches up with what we knew with our minimum. So since our vertex is a minimum, that's another reason why our range is y is greater than or equal to that, not positive 2, that should be at negative 2 since we went down 2. This is looking back at the last example where we went up 2. So we were not adding 2, we were subtracting 2. So let me edit those notes there, since that we were going that down 2 value. And again, that greater than or equal to matches up with the fact that I have a minimum for my vertex. Let's look at our next example. So here we have y equals negative 5 times x plus 3 squared. I want you guys to pause the video and list all of your transformations. So our first transformation here is that x plus 3, which is telling us that we're going left 3. Now I actually have two more transformations. So this negative 5 is telling me two things. The first thing is it's telling me that I have a stretch by 5, and then the negative sign is telling me that I have a reflection over the x-axis. This is in vertex form. Although I don't have a plus k here, I technically then have a plus 0. Well, we would never write the 0 since it's not changing anything, but this can be helpful to help me identify my vertex. So if I were to read this equation, our vertex is going to be at h comma k. Since the general form has x minus h, but my equation has x plus 3, remember I could rewrite that as x minus a negative 3. So that tells me that my vertex then is at negative 3 comma my k value, which we didn't have in this case, so that is just going to be 0 then. Again, we can use our transformations to verify that. So if I start off with my vertex at 0 comma 0, when I go left 3, I'm subtracting 3 from all the x's. so I end up at negative 3, 0. When I apply my second transformation, I'm stretching by 5, so I'm multiplying the y component by 5, but 0 times anything is still going to leave me with 0. And then when I apply my last transformation, we're reflecting over the x-axis, which is multiplying the y component by negative 1, but 0 again times anything is still going to leave me at 0. And so that's a way that we can again verify our vertex. Now that we have our vertex, our axis of symmetry is going to be at x equals that x value, which is x equals negative 3. And to determine if I have a max or a min, I have two ways to think about this. If I think about what that a value is, that a value is negative 5. That value is less than 0, and because that value is negative, we knew there was a reflection over the x-axis, so now my graph, instead of being a U shape that's facing upward, that U shape has been flipped upside down, so instead of having a minimum, we now have a maximum. Our domain again is going to stay at all real numbers. Since my parent function started off with the domain of all real numbers, no matter what transformations we do, we'll still be at all real numbers. And then our range here, let's think about what happened. Started off with y is greater than or equal to 0. When I go left 3, that doesn't change the y's, but when I stretch by 5, I'm multiplying by 5, but that still keeps me at y is greater than or equal to 0, since 0 times 5 is still 0. Then my reflection over the x-axis has me multiplying by a negative 1, so 0 times negative 1 is still 0, but the fact that we multiplied the inequality by a negative flips that inequality sign, so we end up with our range being y is less than or equal to 0 then. Another way to verify that is since we know that our vertex was a maximum, that means that everything is underneath that vertex value, so that's another way that we can get y is less than or equal to 0. And again, that 0 is matching up with the y component in our vertex. Just like the negative 2 in example 3 matches up with that negative 2 in the y component of our vertex. Let's look at our last example. So here we have y equals 1/2 times x squared plus 4. I want you guys to pause the video and solve example 5 on your own first, and then we'll check it together. Let's check example 5. First thing I'm going to do is list my transformations. I have a compression by 1/2, and I also have a vertical shift of going up 4. And those are my only two transformations. Now if I think about this being in vertex form, I have no numbers that are inside the parentheses with the squared, so technically I have x minus 0 squared then. So that tells me that my vertex is going to be at 0, 4. I can verify that by applying my transformations to 0, 0 and seeing where it ends up at. So if I apply my compression by 1/2, I'm multiplying the y component by 1/2, but 0 times anything is still 0. Then my second transformation tells me that I'm adding 4 to all of the y's, so I end up at 0, 4, which matches up with what we could read from our vertex form. Now that we have our vertex, I can always figure out my axis of symmetry. It's going to be x equals that whatever number is in the x spot, so it'll be x equals 0. To determine my max or my min, I can think about my a value. Since my a value here is 1/2, which is bigger than 0, that means that there was no reflection over the x-axis, which we already knew since we listed our transformations, so this graph would be facing upward, and that means that my vertex is then going to be a minimum. So that 0, 4 is the smallest value on this graph then. Our domain, since it's a quadratic, is all real numbers. And then our range, since my vertex is a minimum, then all of those y values are greater than or equal to, and that y component is 4, so my range will be y is greater than or equal to 4. Of course, if we wanted to check that using our transformations, our range starts off with y is greater than or equal to 0. When we compress by 1/2, I'm multiplying by 1/2, but 0 times anything is still 0. And then I'm adding 4 from here, and so I end up with 0 plus 4 gives me 4. Since I just multiplied by a positive and added a number, the inequality sign does not flip, which we already knew because our vertex is a minimum, so we end up with y is greater than or equal to 4. So in this first learning target, we learned what the shape of our parent function is. So for y equals x squared, the graph of that again is called a parabola, and it's a U-shaped curve. We had 5 start points for this parent function so that we could get the entire curve there. We did 2 examples with graphing and actually coming up with what the graph would be. Then we talked about, well, what could I identify from my vertex form in general? And this is really a shortcut way for thinking about, well, if I didn't need to graph, how could I find my vertex, my axis of symmetry, determine if the vertex was a max or min, and find my domain and my range quickly without actually having to graph. And in these 3 examples, we not only applied that general vertex form, but we also looked at, well, if I think about my transformations, I can always use those transformations to verify my answers that I'm reading out of that vertex form.